Hello everyone, welcome to our channel. So we have come up with the new question asked in the GATE exam. So in this, they are asking a question related to the state space analysis. So they given the state space state variable model of the system. Okay. So as we know, this is our A matrix. Like in case of state space model, generally we have deal with the x dot is equal to ax plus bu. This is my state space equation. Okay, so this is a state equation. Let me write here state equation, and by equal to cx plus du. So this is our output equation. So here this is my state, this is my A matrix, this is my B matrix. If you compare with these equations, okay, and this is my C, this is my output matrix C, okay, and D is our direct. Here I have given actually useful data for this all the questions. Here you can see A is a state matrix, B is a input matrix, and C is a output matrix, and D is our feed forward matrix. And one more name we can also call for this D is a direct transmission matrix also. Okay, because there's a direct relation with the between in the input and output. Okay, then only D matrix exists. Otherwise, generally in our practical scenario, uh, D matrix doesn't exist. Okay, for the this it depends upon the system. Okay, and based on the system, whether DMAT exists or not. Okay, all right. So here they given the state variable model, and they are asking about the here they are saying that by is a output, R is a input, and damping ratio zeta, undamp natural frequency omega n of system they want to ask. So let me expand a little bit about the state space analysis. Okay, so basically there are two approaches to the analysis and design of control systems. One is a transfer function approach, and this approach is applicable only to LTI system, linear time invariant system. So it is generally limited to SISO, I mean single input, single output systems. So in this initial condition cannot be evaluated. Generally initial condition are neglected in case of transfer function uh, analysis. Okay, but in case of state variable approach, so this approach, this approach is applicable to linear as well as non-linear system. So and time variant as well as time varying we can also deal with. Single input single output as well as multi input multi output system we can also vary. Okay, so the initial condition in this also we can evaluate. Initial condition also can be considered here. Okay, so if you let me explain briefly here. I'm explain little bit for get some idea about state space. But in a future lecture we will discuss more about the state space. So this is my input at so on u1, u2, and so on u1, and this is my state x2, x1, x2, and so on xn, and this is my output by 1, by 2, and so on by n. So as we can see here, this advantage of the state space. Like in case of transfer function, we can only deal with the single input, single output, but here we can deal with the multi input, multi output, and we can also deal with the our you know uh, initial condition also can be considered here, but transfer function only we can ignore it. But here for this question regard, we require to this state space. First we need to derive what is a transfer function. First we need to derive the transfer function, then only we are in position to find out the damping ratio and unnatural damping frequency. Okay, so all right, this is our useful data. So yeah, they are given here. State representation can be converted to transfer function using this. Okay, where is a bias is a our output, rs is a input. All right. Okay, bias is a output. Okay, and output and rs is our input. Is missing actually in the typing. Rs is a input. Okay, so this is our transfer function. Okay, C into Si, I is our identity matrix. Since this is a second order system, so we can deal with the second order, identity matrix. Okay, and as we know, B and D we already discussed. Okay, and one more thing here, want to like, generally they also ask the S I minus A inverse whole inverse. This also called the state transition matrix. Okay, don't confuse with the A matrix. This is state matrix, and ASI minus A inverse. This is our e the power at. Okay, so this is called the state transition matrix. Generally, in our control system, we can present this same to phi t. All right, so they can also would like to ask this question also, and they more question related to state analysis. They can ask properties of the state transition matrix. So in this lecture, in this we will not discuss and about the properties of state transition matrix, but you can see here these things. I am just taken this portion. Okay, this one. So all right, hope you understood. Okay, we will discuss these things. So here, in case of second order form transfer function here, they given here omega n square by s square plus 2 zeta omega n s plus omega n square. So this is our anti-feedback system. Generally, second order system we can deal with. Here our DC gain is 1. How to find out DC gain? Just put simply s equal to 0. You will get omega n square by s 0. This term also 0. You will get the DC gain 1. Generally, if you write in a more appropriate way, you can also write k omega n square by s square plus 2 zeta omega n s plus omega n square, but k is equal to 1. Sometimes k is not 1, right? Okay, so this is going to change. So all right. So here we need to find, based on our system perspective, we need to find out our damping ratio zeta value. We need to find out on natural frequency omega n. We need to find out. Okay, this is also called the undamped natural frequency. All right. So here, so for this question, this is given the model. First, we need to drive our transfer function. Then after this, we can compare with our this standard second order system. Then we can find out the zeta and omega n. Our intention to find out the omega n and zeta. Okay, all right. So for this, what is the A matrix here given? Let me write here. A matrix they given here 0 1 minus alpha minus 2 beta, 0 1 minus alpha minus 2 beta. All right, let me change the color, and b is equal to the given simple 0 1 0 alpha. All right, this is my input matrix. All right, and A is a state matrix. All right, and C is our output matrix, because output direct depend upon the C. So this is a 1 0. Since here D is not there, so D is simply 0. This is also called the direct transmission matrix. Sometimes people also call feed forward matrix. Okay, So this is some terminologies we need to understand here for D. Generally D rarely used, rarely exists actually, because it's based on the system design. So in a practical scenario, our output directly there no correlation with the one input. Okay. So all right. So here D is 0 for this question. So we need to find out the transfer function. So for this transfer function, as we know, C Si minus A inverse B plus D. Okay. So here I'm not deriving the transfer function this here. Okay. Simply, otherwise is very simple. You can I'm just giving more hint here, like this were you know x dot is equal to ax plus bu by x equal to cx plus du. So here simply you can just take a derivative for this and find out the our transfer function. Okay. So here what is a c value, and first we take a si minus a inverse. This thing first need to solve. Okay, as we know this ever one more thing actually, in case of transition matrix, right? So transition matrix we can say Laplace inverse of this. Okay, let me correct here, like si minus a, this is in Laplace domain, right? So if you take Laplace inverse of this, then it's called the transition matrix in phi t, because it should be in phi t. Okay, this is in Laplace inverse. We need to find out Laplace inverse of si minus a inverse, then get it's come lot of terms come in e the power exponential term. That's why we call e the power at. Okay, so all right, hope you understood this one. So for this si minus a inverse asi, so we can say as 0 0 as and minus a they given 0 1 minus alpha minus 2 beta. All right, and this ever only this is only si minus a. Let me solve it. Okay, so simply we are just addition subtraction of the matrix. So respective term we can add and subtract. So s minus 0, this is s minus 1. All right, and this is minus minus plus, so alpha 0 plus minus minus alpha plus alpha and s plus 2 beta. All right, so for this again we need to take inverse. So for this we have to in our gate exam there was no time to and so take a derivative and drive this find out the inverse. But generally in second order, second matrix order matrix like a b c d, this is a matrix. We find out the a inverse, so straight away we can find out 1 by this is determinant of the a, and this our diagonal matrix just interchange dA, and this one just do the inverse sign change like that. Okay, this comes once we do the direct apply the all rules how to find out inverse of the matrix. Okay, this thing we cannot explain here. Okay, this thing is explained when we you know in the mathematics, like linear algebra we will do all this all this calculation and solve this inverse matrix, and we also extend our properties of matrix. Okay, all right, so here this thing we can apply here. Okay, so let me si minus a, what is turns out here, it comes out here as minus 1. Let me change the color again. Okay, so S minus 1 alpha and S plus 2 beta. Okay, alright. We want to take inverse for this. Then how it comes like, first derivative this our determinant 1 by dt is just take a minus, so S into S plus 2 beta minus minus alpha plus alpha. Alright, and then we are doing our inverse like this, applying this formula as we stated here, direct. Okay, so S plus 2 beta and S plus 1 and minus alpha. Alright, okay, so this is our Si minus A inverse. Okay, then we need to see an Si minus A inverse B. D is not there. Okay, D is 0. So what is the C value here? C value is 0 1, right? 1 0 1 0, and yes, we already know. Just let me solve S square 2 beta S plus alpha. All right, into this our matrix S plus 2 beta 1 minus alpha. Yes, and what is a finally B? B is a 0 alpha, I think so. Let me check again. Yeah, 0 alpha. Alright, what is a B? B is a 0 input matrix. Okay, so let me solve this. Okay, so this term is a like as a constant term. We can, they will not play in this matrix multiplication. So let me change the color. So we can take outside S square plus 2 beta alpha, 2 beta alpha, right? 2 beta not alpha, this is S term. Okay, here you can see, so 2 beta S plus alpha. All right, then we can apply, we can, so first we can multiply this, otherwise we can multiply this also, then we can later we can multiply C. So this one we know the how to multiply the two matrix. So this one we just multiply this, okay, and this one, and then added, so it will coming out, this is 0 alpha. Okay, and minus alpha into 0 0 S alpha. Okay, then finally S square plus 2 beta S plus alpha, and again we can multiply alpha, and this is 0, then we can multiply, we get the alpha y S square plus 2 beta S plus alpha. This is our transfer function. All right. So we find out transfer function. Then we need to find what is the question they want. They want to damping ratio and natural frequency. So we need to compare with our standard second system, a1 square y s square plus 2 zeta omega ns plus omega n square. So what is the omega n square? Directly we can compare it here. Omega n square is equal to alpha. Let me change the color again. All right. So omega n is equal to under root alpha. Okay. Here we take only positive value. The least coming roots will be compared with alpha, but because of the system should be stable, so omega n is equal to positive value. We can take it. Okay. Otherwise, in a real case, because this is a frequency, right? So frequency should be positive, negative. There is no like practical possible. Okay. All right. So here, then 2 we are comparing it, right? 2 zeta omega ns, 2 zeta omega n is equal to 2 beta. 2 cancel out, zeta is equal to beta by omega n. Alright. So zeta is equal to, what is a beta value? Beta is a nothing but omega we need to find in terms of alpha. So we get zeta beta by under root alpha. Alright. So finally this question be solved. Okay. We have this solved actually. So what is the answer actually? Zeta value, omega value is under root alpha. Omega value is under root alpha, and I think this will be correct, beta by under root alpha. Okay, and omega n is equal to under root alpha. Alright, so I think A option is correct. Okay, beta by under root alpha, omega n is equal to under root alpha. Okay, beta by under root alpha. Okay, so this option is correct. Okay, so for this question it has been solved. So and they can also ask the our for this question they ask the state transition matrix. Okay, state transition matrix. But the question just I am doing here. What is the state transition matrix? Laplace inverse of the Si minus A inverse. Okay, this thing we already calculated here, na? Only we need to do the Laplace inverse. Okay, so what is a Si minus A inverse? This matrix, right? You can see here. S plus beta, S plus 2 beta. Okay, plus 1 minus alpha S. We can also write phi t minus alpha. Yes, all right. Okay, and 1 by S square plus 2 beta S plus alpha. Okay, so for this we need to do the Laplace inverse of each term. S plus 2 beta by S square plus 2 beta S plus alpha, right? And 1 by S square plus 2 beta S plus alpha minus alpha by S square 2 beta S, okay, plus alpha S by S square, okay na? Then actually here like we need to apply the Laplace inverse rule here. So how to apply here? Here you can see S by S square plus 2 beta S plus alpha and plus 2 beta by S square plus 2 beta S plus alpha. Okay, so you can see here, but here we can see like that S plus, we want to this whole square actually, so S square plus 2 beta S and plus beta square minus beta square plus alpha. Okay, so yes, plus beta whole square, all right, minus, yeah, we can say alpha minus beta square. Okay, so like that we can follow here. So this term is coming like that, cos, as we know cos omega t, what is a cos omega t ut, what is the Laplace transform, s by s square plus omega square. Okay, but beta here is there, this is like uh, we can say delay. Okay, we will discuss these things, but here you can straight away you can remember it. Okay, cos omega t. So here we can get this in terms of Laplace inverse in terms of time domain for this term. Okay, so we can get here e the power minus beta t into cos omega t. Omega this is square, so a under root alpha minus beta square. Condition provided here, alpha minus beta square greater than 0. Alpha always greater than beta square. Alright. So this kind of condition there. Okay. And similarly this term is going in a sine conversion. Okay. So how to calculate it? Just I am taking here. Let me change the color. So they can also would ask, this state transition matrix. So this term is 2 beta by a square 2 beta s plus alpha. Alright. So we can explain the same way, 2 beta s plus beta whole square alpha minus beta, sorry, alpha minus beta square. Alright. So as we know Laplace of the sine omega t and ut is equal to omega by s square plus, let me change the color so that you can, omega by s square plus omega square. Okay, so this thing we can do for this, but beta is also there, so e the power minus at sine omega t ut is coming omega by s plus a whole square plus omega. This is like a delay. Okay, we will see, discuss, no problem, we will see these things property when we discuss about the Laplace transform. So here 2 beta by s plus beta whole square plus a man alpha minus beta square. So what is the Laplace inverse of this term? Is coming 1 by alpha minus beta under root, right? And then e the power minus beta t into sine under root alpha minus beta square. Okay. Okay. So finally complete term would be e the power minus beta t into cos under root alpha minus beta square. Okay. And plus 1 by under root alpha minus beta square into e the power beta t into sine under root alpha minus beta square, like that. So same term this also there, 1 by s square plus 2 beta s plus alpha. So for this we can find out the same term we can apply here, 1 by same thing. I am explaining how question can be framed in the GATE exam. So there is no need to solve more question, but once question we need to apply all possibilities. We need to outline the out possibilities. So here s plus beta whole square here before this here 2 beta also there, right? So we just multiply 2 beta also here. Okay, so here we can see 2 beta also there here. Okay, so here s plus beta whole square plus alpha minus beta square. So we can find out the Laplace transform this s Laplace transform s function. So we can say 1 by under root alpha minus beta square under root and sine inverse sine under root alpha minus beta square into e the power minus beta t. Okay, and this will be unilateral, like u2 be to multiply. Similarly we can find out this also, and this term is same, right? This term and this term is same, so we will get the same value e the power beta t the power minus beta t into cos under root alpha minus beta square. Okay, so one term is remaining, this one is minus alpha by s square per 2 beta s plus alpha, but this equation is very lengthy, so that's why they didn't ask this big question actually. Beta s plus alpha, they can give the numerical value alpha and beta, right? So no problem. So here this again coming in the s function, so we can write alpha s plus beta whole square alpha minus beta square. Okay, we can write what is the Laplace domain, Laplace inverse 1 minus alpha is 1 minus beta, sorry, alpha minus beta square into sine under root alpha minus beta square into e the power minus beta t ut. Okay, so here we can write the our state transition matrix e the power matrix. What is this term? This term is same, right? What is the term actually for this? This term e the power minus beta t into cos under root alpha minus beta square. Let me change color, right? E the power minus beta t cos under root alpha minus beta square. Okay, plus 2 beta under root alpha minus beta square sine under root alpha minus beta square and e the power minus this term will be always there beta t and whole multiply the ut. Why ut? Because this is a unilateral, the ROC will be lying in a right S plane. Okay, we will discuss what is ROC of the Laplace domain and what is this term. This will be 1 by s square per 2 beta s plus alpha. So this will be this term. I don't think so this type of question they will ask, but still we should know. Question is simple but calculation a little high, but okay. Under root 1 beta square sine under root beta square into the power minus beta t. Okay, and ut. Then this question, this will minus, yeah, minus alpha by under root alpha minus beta square sin inverse under root alpha minus beta square into e to the power minus bt ut. Alright, and last term is s by this term. This is same term, na? S by s square plus 2 beta s plus alpha. So this will be same, means this value, this term. Okay. So e to the power beta cos under root alpha minus beta square. Alright. So this is our state transition matrix. Alright. So we have solved the state transition matrix. We have already solved what the question they given. Okay. So we will not stay this question much. We'll discuss in our future videos. So that's all for this video. Anyway, this video goes long. Okay. So please, if you like our contents, please like the video and share the video and subscribe our channel. So that's all. So thanks a lot.